as it comes to our next speaker, if you're eager to listen to some implementation details of popular libraries, our next speaker will give you a comparative analysis of them. As you see, he's already taking his position. So, as you know, at times you gotta wait pretty long to get results and to see if your program works. Now, if it doesn't work, then it gets even, you need more time to see why it doesn't work. And with all this, times flies by. And what we want are faster results. So, our next speaker, who's standing next to me, Mateusz, he is a senior Scala developer. I got to put in here that I also asked him about his favorite game, and again, it was Assassin's Creed. Somebody else said that, so you have to probably know which one. How you guys doing? Okay, just still a second. So Mateusz Kubuszok, he, as I said, senior Scala developer.
Yes.
Yes, exactly. And as you see, speech title. You're ready, right?
Almost.
Almost ready. Slow auto, inconvenient,
Just
semi.
to make sure that...
You want to make sure? Okay, you tell me, I'll just get off stage. You're ready?
Yep.
Okay. We need a big round of applause for Mateusz. And you're on.
Thank you. So, most of you probably use some Scala library which was based on typeless derivation. Maybe some of you don't know it, but you probably did. Also, most of you probably started using this library using something called automatic derivation, then got burned out once or twice with this approach, started moving on to something else called semi-automatic derivation, which seems a little bit clumsy. And a lot of senior developers basically know that there's this choice between things that bites you or things that is clumsy. So in this presentation, I'll try to show that those issues are not some inherent issues with derivation in Scala. There are more issues with how we approach the derivation in Scala and that we can change it. Basically, we're doing derivation wrong and we can fix it. So a little bit about me. I've been working in Scala for the last 9 years. And 7 of these years I was working on Chimney, which is like a really macro-heavy derivation library, which taught me quite a lot about the stuff that I will be talking about today. I was also like blogging, speaking at the conferences like this one. Also wrote a little ebook about JVM and Scala, so I think I know a thing or two. But also a trivia, I am not a Kubuszok. Kubuszok is Jakub Kozłowski. Hi, fellow. Just a trivia. So enough about me, so let's talk about today's game plan. Our agenda. We will start briefly talking what is a type class. Most of you should know what it is, but some of you might not. Then we will explain what is the type class derivation, because it has nothing to do with calculus or integrals. So some of you might need to learn about it. Then we will tell a little bit what we mean by automatic and semi-automatic derivation. In particular, if we are copying the series approach. Then we see that not all the libraries are copying the series approach when it comes to semi-automatic derivation and also automatic derivation. And hopefully by the end of this talk you will see that how the author chooses to implement their library impacts you as a user. And this is very important because in this talk I do not want to do any sort of tutorial for shapeless, magnolia, macros, mirrors, or whatnot. We will only talk about someone else make the decision when they're implementing the library, how it affects you as a user. So if you want to take a look at all the code that generated the numbers that we'll be discussing today, you have a QR code. I will be showing this QR code again at the end of the presentation, so you can study the code at your own leisure time, because we simply do not have time to look at all of that. We only want to look at the outcomes and the results. So let's start. What is a type class? As far as I can hear is an interface, but this interface has to have some type parameters, and every single implementation of this interface that we care that they should be separate is implemented for a separate type parameters so that we can all distinguish them just by looking at their type. And because of that, compiler can provide it for us if we just tell it, give me this thing of this type. So for instance, let's say we have some type which is representing JSON as a data. We want to encode something as JSON, so we could define basically an interface which does the encoding. We could define several implementations of this interface, put it into this thing called implicit scope. Then when we would use, for instance, extension method and try to use it like that, then compiler will just find those implementations because we annotated it as something to be found and provide to the place that we need this interface just based on the type. And that's the most popular way of using this type class thing and this implicit in Scala. However, here we only we have provided implementation for string in double. What if we have some types defined on our own, like this one, and if we try to encode them as JSONs? When the answer is that the compiler would fail to provide those implementations because there are no such implementations. Like, it cannot pull them out of the thin air. Or can it? This is where the so-called derivation comes in. So basically, what I want for you to remember about the derivation, you can study all these nice little graphics on your own time, at home, on your own leisure. We will just be skipping over them. What I want you to remember about the type of derivation is basically this idea that we have some type, usually case class or filtrate. We have implementations for smaller parts of this type, and someone somehow combines them together to give you the implementation of the whole. So, for instance, if we look how Circe does it for this thing called encoder, we have this encoder, we have this extension method, we have those case classes that we would like to encode as JSONs. The library author assumed that, okay, let's do it this way. Every field that this case class will be, each of those case classes will become a JSON object. Each of the field names becomes a key name inside this object, and the values will be encoded by the encoders for each of those fields. So if we wanted to generate the encoder, which would do exactly the thing that we want to achieve, encode those case classes, it would have to put together the implementations for each of those fields, add the names of those fields, slap them together, and bam, we have the encoder. And Circe allows us to do it in two ways. The first one is called automatic derivation. Basically, the idea is that you add a single import, and that's it. Compiler does everything for you because it does some magic with implicit scope that whenever you're trying to get the implementation of this encoder, it first looks, have you done it yourself? Like, have you implemented this interface yourself manually and put the implicit scope? If not, as a fallback, it will use some magical mechanism which will put things together if it can. The other approach is so-called semi-automatic derivation. And the idea here is that, okay, we will not provide things magically for you. You have to define those implicit yourself, but we will give you some magic method which will generate the body, basically generate this value that you could just put into this implicit. And this thing is quite useful. It has this built-in mechanism preventing you from having this circular dependency, because even if we can see that there's this implicit address encoder and implicit user encoder, the derived encoder method will not return it even though it sees in the scope. It will ignore whatever it sees, and it will just return a new value. Okay, so it will try to analyze how this automatic derivation works for the example of the address. It's just a single case class with a single field. We take a look at it. So we could if we analyze the whole diagram, we would see that it's first try to see if we define this encoder. There is no such a thing, so as a fallback, it uses magical mechanism we got by this magical import. This magical mechanism goes through all the fields. It happily found all the fields, encoders for each of those fields because there's only one field. It generated the encoder, and bam, we have this thing that is allowing us to encode our address. With the semi-automatic derivation, it looks almost the same, except that there is no fallback. It doesn't try to look if we created this implementation. It goes straight to the process of creating this implementation for us anew afresh. So far, the only difference we can see is this fallback part. But if we looked at the user, where user is having inside of itself another case class, and that another case class does not have defined this, implementation. So it will generate those implementations for those nested case classes as it tries to resolve things, and so this diagram starts to look more and more complicated, and all of that happens without you even knowing it. On the other hand, semi-automatic derivation looks much simpler. Why? Because when you have this implicit for user and it tries to find an implicit for address, if you haven't defined that implicit yourself, the derivation will fail. Out of the box, semi-automatic derivation is not recursive. You either have to define all of those intermediate implicit yourself, or you have to import both automatic derivation and semi-automatic derivation. So things look a little bit nasty, but for some people are using it.
Can it be bigger?
Unfortunately not. Okay, but you might ask me, okay, where is the code? I would prefer to look at the code. It's easier to read some code than some weird slides because I'm a programmer and whatnot. And my answer to that is that first, we are focusing on the user side of the derivation, so we will be only using at how we would be using this library, not how they were implemented. Two, you can always look at the code here and study it. And three, if we really wanted to have this experience of analyzing all these shapeless, Magnolia, macros, mirrors, and whatnot, we would be spending next half the conference on looking at the code, and by the end of it, you would understand absolutely nothing more, and we still would not get to the point I'm trying to make. So let's get back to the main topic. Why people even bother with making the distinction between automatic derivation and semi-automatic derivation? Because why we just don't use automatic derivation for everything? It looks simpler. So first reason why we might use semi-automatic derivation is that if you want to make sure that every single place in your application is having exactly the same behavior when it comes to something, the easiest way to do it is having just one implementation. So you define the thing once, put it into some value, and every single place uses it. So we're not going to challenge this reason of using semi-automatic derivation. But there is also another reason why people are telling you to use it: speed. So there were a lot of horror stories that someone was using CRC and suddenly they discovered that their one of their modules with just a single file were compiling for 5 minutes or so, which is completely killing their productivity. They're completely annoyed at that, and they spend a lot of time with profilers, flame graphs, all of that stuff to figure out that the only reason they have this is because they use automatic derivation. And if they derive things by hand with semi-automatic things, suddenly it compiles in a few seconds. But is it still true today? So to check that, I designed a little example. I have some really mean case class. You don't have to worry how it looks like. All you have to know is that it's 5 levels nested case class, where each nested case class contains more fields. The amount of fields at the bottom is like a factorial of the amounts of levels. So it stresses our compiler a little bit. we will try to use Circe to do some sort of round trip. So we were get case class, try to encode that string, as JSON, then decode the JSON back to our original case class to, for instance, check if this implementation is correct, so that we will get the same case class. Or we can use some benchmarks, like how long it takes and to run, or how long it takes to compile. And then we can compare this code to the code which derives things semi-automatically, as opposed to just using one single input, which makes this code a lot easier to maintain. So this shouldn't be hard on the compiler. It's just few nested case classes. So how hard can it be for the compiler? So I put some work to measure how long it takes to compile those things. We'll have just a single file with a single derivation in a whole module. So all these times that you are seeing here is the compilation of a single file composing basically of this code and the main. And I did it for hot JVM, which simulates how you would have it when we would be developing this code, and on cold JVM, which is something that you are always getting. We are using CI, because on CI you are always starting as BT or whatever afresh. And we can see that basically on Scala 2.13, the differences, well, there is some optimization, but the differences aren't that huge. On the other hand, on Scala 3, this single file could compile as long as 46 seconds on cold JVM. So this is kind of, upsetting. Especially when you see that optimizing it by hand suddenly turns it to 10 seconds on cold JVM. And if you are having warm JVM, you can go down with this semi-automatic derivation to 1 second. So on Scala 3, huge differences. On Scala 2, small differences. Kind of weird, but maybe we'll figure it out. How about benchmarks? Well, when it comes to benchmarks, again, there are some differences on Scala 2.13, but they aren't very big. You could assume this is like an optimization, but it's like, I don't know, 10%, something like that. But on Scala 3, you can see that the performance of the automatic derivation is basically abysmal. It's like an order of magnitude slower, while semi-automatic derivation is already slower than what we have on Scala 2.13. So something is happening here. And we can actually try to explain those things. Basically, the author of Shapeless that started all of this mess with type-class derivation also wanted to spend a lot of time so that his invention would be quite performant. So he started one PR, then another PR, then finally third PR get merged, and fourth PR also get merged. And those PR, well, he was boasting that he basically managed to optimize it a lot, like an order of magnitude faster. And the work he was doing was basically about reusing the results from previous derivations so that there will be no overhead and stuff. And we can see it on Scala 2.13 because those both compile times and runtime aren't that much different. So we can basically assume that the code that is generated is very, very similar, but it doesn't translate to Scala 3. Probably because not all of these optimizations were migrated yet. Probably because mirrors work kind of different way than Shapeless. And also it's quite important to know that those things were not yet merged in Scala 2.12 because the first PR got merged, if I remember correctly, Scala 2.13.0 milestone 5. So just before release of Scala 2.13. So whenever you hear people telling you that automatic derivation is absolutely the worst, probably they are basing this on their experience from Scala 2.12 and before. Or Scala 3, as we can see. Okay, so did someone try to improve the performance in some other way than automatic or semi-automatic derivation? Yes, there did. There's this library called Magnolia, which is like an alternative to Shapeless or Mirrors or Scala 3. It's both about better API, better performance, better compilation time, and better error messages when the derivation fails. So let's start with the last claim. If we look at all of the error messages, we created this nice little nested case class. We tried to encode it in one go. And we, on purpose, make sure that the field in the most nested one cannot be converted because this type is not handled by anyone. So what would be the errors returned by each of those libraries if we use semi-automatic derivation? Shapeless would tell us that we couldn't find implicit for encoder of this most nested object. Okay, at least we know for which object it failed. Mirrors would tell us that we are missing an instance for the type of this field that is wrong. So, also kind of nice. Magnolia, however, would tell us something like, could not find encoder for the type in the parameter of the name, this and this. So we would exactly know for which type it failed, for which field, and in which case class. So it's really useful information. However, we can overestimate this impact because if you use automatic derivation, all three of those libraries would just tell you cannot find an implicit. So if it comes to Magnolia and how it helps you debugging your issues, it only works with semi-automatic derivation, sorry. So how about the compilation times? Again, something interesting is happening. So both automatic and semi-automatic derivation on Scala 2.13, compile times are almost identical to using Shapeless. Perhaps on Scala 2.12, before all of these optimizations, it would be better, but on 2.13, very, very little differences when it comes to how long you have to wait for the results. But on Scala 2.3, you can see that the compilation times are even worse than if you are just using mirrors. Probably because on Scala 3, as opposed to Scala 2, Magnolia was implemented with mirrors. So whatever overhead mirrors had, Magnolia just adds something on top of it. On the other hand, if we run benchmarks, we can see that, again, all these approaches on Scala 2.13, very, very similar performance. On Scala 3, on Scala 3, Magnolia seemed to behave better for semi-automatic derivation. So it does some improvement over using raw mirrors. But it's even worse than abysmal times of automatic derivation for CSV with mirrors on Scala 3. So it's like 2 orders of magnitude slower than semi-automatic derivation. So that is kind of worrying. Probably something you would like to know if you try to use these things on production. So as far as I can care, that whatever you use, Shapeless, Mirrors, Magnolia, whatever the library maintainer is using, Shapeless, Mirrors, Magnolia, it doesn't affect you very much. The bigger difference is whether you're using Scala 2.13 or Scala 3. So is there something else we can try? Well, we can take a look at some other libraries other than CRC, like JSON Scala. The author of JSON prioritized performance like it's everything. And because performance is so important, we want to avoid allocations, and having all those intermediate implementations for these intermediate types means that we would have overhead, so it does not have automatic derivation at all. But if you're thinking, okay, so do we have to always write every single implementation like with derive codec or derive encoder for every single intermediate value? Well, apparently not. So let's take a look at it a bit closer. If we try to use this code with Shapeless, you can see that we have one implicit defined. Not implicit for each of those nested structures, just one implicit for the outermost one. And the rest is just a difference in API between CRC and JSON eater. And it compiles. It works. It does what it should. If we try to analyze how it is generated, then we would discover that basically this semi-automatic derivation is recursive. And if we try to read how this recursion works, it looks much more complicated than what we have with Circe, probably why most people are using the approach like in Circe. But if we zoom out and not look at all those small letters just in the bigger picture, first thing we can see that Circe approach looks much simpler, so probably why people are copying it. But the other things we're noticing, this is happening probably because in Circe, we still have to do this searching, recursion, combining of stuff, kind of loops. But we dump all of that on the compiler and doing that for implicit scope, while inside JSON, it's happened like explicitly. We're writing literal if-elses and like for loops and recursions. So we take that complexity upon ourselves, so it starts being visible, but it's not an overhead because we are no longer doing everything through several layers of the compiler and type checking. And it might have some impact of user experience, like I hope. Otherwise, like what we are talking about all that crap. And as you can see, compile times for JSON iter are always better. Scala 2-13, Scala 3, it's always better, sometimes slightly better, sometimes more better, but basically, improvement in the compilation is huge. It's noticeable, especially when you compare things to automatic derivation in Scala 3, then, But the real killer is the difference in the runtime performance, because all the code is generated all at once, recursively with no intermediate structures, and also other optimization that JSON iter is doing. But thanks to all, basically because we are generating all the codec for all the nested stuff at once, we are able to do optimizations that we wouldn't be able to do otherwise. And we can see that it's run, comparing to Circe, with an order of magnitude better performance. So it's kind of nice. But again, we would still improve semi-automatic performance, semi-automatic derivation. Could it be automatic so that we would be as simple to use as Circe automatic, but with better without all of the issues that Circe has? Well, in my own library in Chimney, we had exactly the same issue. We wanted derivation to be recursive so that we could optimize stuff. We wanted to use instances provided by the user only to override the behavior, not to drive how we define everything, but only to override. Everything that is not defined by the user, we're going to the defaults, and defaults can be resolved internally, recursively within a single macro derivation. And we also wanted automatic derivation because that's the only way to make the library approachable to the newcomers, but without getting back to all the issues that Circe has. So we obviously have to come up with a solution, and basically a draft of the solution is here. You don't have to analyze it right now. All of such code is easier to understand once you can get back to your home, poke around it, give it some time to approach it. Basically, what we decided to do is to have two types. One of the types is intended to be used by the user, and the other is intended to be only used to provide automatically derived implementation. Then extension methods would try to use user's value and then fallbacks on automatic values. And macros, while generating all of that stuff, would never, ever try to call itself. It would only use the implicit that you have provided, never the implicit. It would never call itself automatically, because that would get us back to Circe or back to Magnolia with automatic derivation. And we achieved that basically by the separation of those two types and subtyping and stuff. If you are curious how it is work on Scala 3.7 and the changes to the givens, talk to me after this presentation. We don't have that much time to discuss these changes, but let's move on. How it impacts you as a user, because that's why what you are interested in. So we want to test outside of Chimney, ideally like making JSON eater able to use that stuff, but we cannot use JSON eater's code because it's someone else's code and they don't really like automatic derivation. So I decided to write a wrapper around JSON eater. So I'm using all of the code that JSON eater uses, I'm just using it with my own types. And because it was easier, I implemented it only on Scala 3. With this wrapper, you can see that I have a just single import. Then I have code which looks basically like a JSON eater. So all of that should give you the same user experience as automatic derivation with CRC, right? So if it would be able to give you those compile times and runtime performance and no issues, just like semi-automatic derivation, but still being automatic derivation, well, that's why I call it sanely automatic derivation, because you're not going insane while trying to fight it. So I run the benchmark for this wrapper, and it's this Tiffany blue bar on the right. You can see that it's only slightly overhead over semi-automatic derivation in JSON eater. Basically, it looks the same when you look at the worm JVM, and it's much faster than semi-automatic derivation on CRC, and obviously much more faster than automatic derivation on CRC, so you get all of the benefits and none of the drawbacks. How about the benchmarks? When we look at the benchmarks on Scala 3, because I only implemented it for Scala 3, basically the numbers are almost the same. So you cannot even say that, okay, we're making a trade-off between compilation time and the runtime performance. No, you're not sacrificing anything. But then again, you could say, okay, this is JSON eater and this is CRC. Those libraries have different philosophies. They have different internal implementations and whatnot. You're comparing apples to oranges. Could you give us some more fair comparison? And yes, I can. If you know the thing called show type class from CRC, it's basically toString on steroids. So I decided to implement something like this. The only difference is that there is this like variant of show, which is called show pretty, which do all these nice indentations, so the code is much more readable. So I also did that. And just for the heck of it, instead of concatenating strings, I decided to use string builder so that I would also save a little bit of performance if I was using it. And you can see how it should be used. We have this nice little nested case class. We just call show pretty on it, and we should get this really nice indented output, which should be very easy to read. Amazing thing if we would be using it in login and whatnot. So I decided to implement automatic and semi-automatic derivation with shapeless on Scala 2, automatic and semi-automatic derivation of this class with mirrors on Scala 3, the same thing for Magnolia, Scala 2 and 3, and finally I would try to use this sanely automatic derivation with macros, delegating some of the stuff to Chimney macro commons on Scala 2 and 3. So what are the numbers? Yeah. So our first approach is that numbers are not really bad, but you see this macro works much better than automatic derivation in Scala 3, but other than that, slightly worse than what we have with other stuff. Runtime, again, not good, not bad, but not the greatest. So what is the failure experiment? Like, well, it should be better than automatic derivation on Scala 3, but still, for other approaches, it doesn't look very good. Well, that is until you remember another thing. JSON had this little trick that when it had to reuse the code for the type that it derived how to encode or decode or whatnot, then it found the type again. It wasn't like running the derivation again internally. It was just shoving all of these things into depths defined inside your type class. So that for each type, the code would be derived only once. So it was a single PR to our previous approach, how it changed things. Would that make a difference? Well, yes, it did, because right now we have the fastest code on all versions of Scala, whether we're comparing against automatic derivation or semi-automatic derivation. It's called JVM, hot JVM. It's the fastest to compile. It's the fastest to run. And as a bonus, we haven't been talking about debugging macros because people are usually afraid of them. So I did again the experiment when we are having the field that cannot be derived for, and we're able to give it a real nice information that is not neither built-in nor there is any implicit for this field. You can fix it, and we can fine-tune this error message as many times as we want. And also, because the best way to debug things, if we look at the logs, we can also start logging from the macro and be able to look at all the code inside IntelliJ or Scala meters or Scasti. We can just look at the logs from the macro and see exactly the logic in each step of the way. And this tells us exactly when things went wrong or right. We can measure time of the derivation. We can show the whole expression, whatever. We can do everything there and help our users. Like, sky is the limit. And with that said, I'll start to wrap up. I have to start wrapping things up. So last year, developer survey from the Virtuos Lab showed that 53% of the developers were complaining about the compile times. And that there should be some effort from the compiler team to improve this. And I believe perhaps it's not the compiler team. Perhaps the issue is that our approach to derivation was wrong all along. We were simply using libraries and derivation in such a way that we imposed such an overhead of the compiler that no amount of the optimization could help. As you could see, several years of work of Miles Sabin optimizing Scala 2.13 could be wiped out by a single PR to a library with optimization which didn't even do any sort of profiling. It was just, okay, let's use devs. Bang. So perhaps we should rethink how we are doing our derivation. And this is something that should be done by the library maintainers. And so I hope that you, as library users, would start giving library maintainers feedback in a polite and respectful way, that you are valuing the compilation times, you're valuing performance, you're valuing good error messages, so that they will see the value of improving things. And also, we cannot just say that all of the time spent with Shapeless, Magnolia, Mirrors, and whatnot was ill-spent. Because if we think about it, if not for those libraries, we wouldn't have faster libraries. If not for those libraries, we wouldn't have those libraries at all. Because they create this entry-level, as much as possible for metaprogramming, way of people to starting doing those libraries. But now that we need those libraries to be production-ready, it's time for those developers to learn to improve their game. And with that said, I hope that you like my presentation, and thank you.
Thank you very much. Thank you, Mateusz. Really pressed for time, but Mateusz is here for the rest of the day, so you can catch him and ask him questions during our next break.